Welcome to Ask and Learn.
You may want a satellite to orbit over the same point on Earth over and over again for whatever reason, maybe for broadcast purposes or for monitoring purposes. But this is known as a geostationary orbit, and usually those are in the equatorial plane. And the idea is that the orbit has the same period or the angular velocity that the Earth does, where that velocity is 2 pi over the period, and the period is 1 day or 86,400 seconds. Um, and so we are going to find out how far you would have to put that orbit. Okay, that's not a very good circle. We're going to figure out the radius of the orbit in order to get the period to be correct. And it's good to start with some basic physics, that in order for something to move around in a circle, the centripetal force has to equal the mass of the object times the centripetal acceleration. This is Newton's second law. But here we're really talking about the force of gravity. So that's big G times the mass of the orbiting object times the mass of the Earth over the distance squared is equal to m omega squared times r. And we can see that this is going to result in one of Kepler's laws, but with very specific constants in it. So what we're trying to do is solve for the radius given the period, and we know that the period is related to the omega squared. So we get that r cubed is 1 over omega squared, and we can put in for the period. Oh, and let's see, the mass cancels, thank you. The mass of the orbiting small object cancels, but not the mass of the Earth. So yeah, so we get Kepler's second law, third law, get my laws right here. This is Kepler's second law, and it arises naturally from uniform circular motion. So if we know the mass of the Earth and we know G, we can certainly find this R. And we'll go ahead and take a cube root. Yeah, there's some big numbers, but we'll show what goes into here. And yeah, it can be tricky to do these exponents. The mass of the Earth is roughly 5.98, 5.97 times 10 to the 24th kilograms. And of course, the period in seconds is 86,400. And why we have to put the period in seconds is I have big G, the constant big G, in terms of SI units. And of course, 4 pi squared is just 4 pi squared. And this winds up to give about 4.22 times 10 to the 7th meters. And we'll write that in kilometers, and it might be a little bit easier to interpret. The moon, by the way, moon orbits at approximately 4 times 10 to the 5th kilometers. So we can see that a geostationary orbit is about a tenth of the way to the moon. And I'll say approximately, not exactly. Okay, and one last thing. What if instead of going around the equatorial plane, what if the satellite starts at the pole? How long will it take to get to the equatorial plane? And we can see that that is 1/4 of the orbit. So you can send a geostationary orbit around the poles, and then of course it's not geostationary; it's a polar orbit. Um, I'm not sure why you'd want to do that. It's sort of destroying the reason for making it geostationary, or putting it at the place where it would be geostationary, but it would take 1/4 of a day. Um, so basically 6 hours.